All right, we're going to continue our discussion of rasterization today. We're going to get into triangle rasterization. So, a lot of you guys are having trouble with rasterizing a line. Here's one way you might think about doing it. And we've got point one, point two. Obviously, I'm not copying over all the code here for you. I'm just going to kind of show you. So we can figure out how far apart two points are by using hypot. That's the Pythagorean theorem. And I can also figure out how much it goes up and how much it goes to the right from one to the other. And then that could be negative, I believe, as well. And then instead of looping across all the rows or looping across all of the columns, what I do is I loop across all of the units and the distance of it. So if you have a triangle that has a hypotenuse that's 12 units long, 12 times, I'm going to step in the direction that we're going. And this works with positive numbers. This works with negative numbers. I don't have to swap points. I know Raymond is having issues like if the maximum x was smaller than the minimum x, he was swapping it, but that doesn't work with the y's because the y's also could be inverted with a max x smaller than the minimum x. And I think his code barfed on that because there's four possibilities and you have to start special casing it. This is all it took for me. So you might, I don't know if you're going to cry now or be inspired, but that's the line rasterization algorithm I use at least. There's no anti-aliasing on this. I know I have a version on here somewhere where I am anti-aliasing it. I just don't know where it is. So, cry and inspire. So yeah, and I do have some safety measures in here just in case it's going off the edge of the screen. So I'm clamping it to the edges of the screen if I care about that. So basically, yeah, let's say that you're going like you have a vertical line, which is not something you can draw very easily using line intercept equation, y equals mx plus b. Here it handles it just fine, right? Because our destination, our starting column and ending column are going to be the same, so that's going to be 0, so the run's going to be 0. The rise is going to be like 10, it's 10 units up. And then that'll be our starting and ending column and row. And so what we do is we draw a point at our starting row and column, and then we just say 10 times we're going to move 1 unit in the direction we're going. So if the rise is 10 and the distance is 10 because it's 10 up, then we move up 1 pixel at a time and draw 1 up, 1 up, 1 up, 1 up, 1 up. We do that 10 times, and we're done. And this works if you go up, if you go down, if you go left, if you go right. You don't have any special cases you have to worry about. The only thing really missing from this is anti-aliasing. And what there's actually been some very clever implementations of anti-aliasing in the past that aren't as important these days because computers are faster. The one that most people study is Bressingham's algorithm. And basically, as you go in a direction, you can sort of accumulate. You can kind of accumulate how far down. Like let's say on this one, right? You got, it's going down 1 every 2, right? So every time you go 1 to the right, it's like you're going down a half, and so you're like kind of accumulating how much, every time you're going down half a pixel every time. And so what you can do is you can actually use that to anti-alias. You can know how much you're towards the next row down or how much you're towards the next row up if the slope is positive. And then you can draw 2 pixels, 1 on the current column, 1 on the column below it. And so like if you have a slope of 1/4, negative 1/4, every 4 pixels you go to the right, you go 1 pixel down. So what happens is on the first one, you just draw a solid pixel. On the one to the right, you draw a pixel, 75% intensity on the current column, current row, 25% intensity on the column below. Go to the right, it's 50-50. Go to the right, it's 25-75. Go to the right, it's 100% on the next row down. And then you repeat. And so basically you're kind of drawing two rows at a time and it'll just kind of stair step down. That way you'll end up with a nice anti-aliased thing. Wu's algorithm, yeah, actually that's perfect. Okay, so you can see how this is working. That's actually exactly the No, except it's 5. It's 5 pixels. So every pixel it goes to the right, it transfers 25% of the intensity to the column below it. And so you can see we start off with a full intensity pixel here. We go 1 to the right. We've accumulated 20% into the row below us. We go to the right. We accumulated another 20%, another 20%, another 20%. And then we get a full intensity one here. And this algorithm has actually been implemented in assembly in x86. Very, very fast. This is actually like one of those things like you'd buy like Abrash's Black Book, and I'm pretty sure it'd be in there. I don't remember off the top of my head. But these kinds of algorithms like that they get implemented. Yeah, there you go, Macaulay Brush. Yeah. Maybe it's not his Black Book. Then. By the way, the full copy of this book is available online. What is the copyright on this? What was it like working on Quake? Okay, so this is actually after the. Okay. So Abrash ran a column in a journal called Dr. Dobbs. I actually read it when I was a kid. It's not around anymore, unfortunately. But it was like a magazine for like computer nerds, and so I wonder if there's a copy of this. There you go. All right, and so. So Abrash had a column in Dr. Dobbs' journal, and quite readable. Dad, is that fried chicken? I don't think so. I think it's stewed chicken. It looks like fried. Yeah. So they're quite readable, and it comes with source code and explanations on it and stuff like that. And so I think that if you wanted to use Wu's algorithm or the Bressenham algorithm, more power to you. But I don't know. This one works for me, and it's small, and it gives you solid lines. Like you don't get gaps in it. Do you have a list somewhere of the reference books that we can use? Yes. So Abrash's Black Book. I don't want to say that it's dated because it is, but it's not. So a lot of the tricks that he discusses in it are for like 386 processors and 486 processors and squeezing every last ounce of performance out of a 486. And modern Pentium CPUs oftentimes just have better options than these super tricky, assembly implementations. But the philosophy that Abrash brings to the game is really good. Like he writes an algorithm, it's not fast enough, so he rewrites it and he tells you like, here's how I rewrote it. And then I'm going to rewrite it again. He shows you iteration 1, iteration 2, iteration 3, iteration 4, and like his thought process on how do I make this faster and faster and faster and faster. And that's timeless. The notion of like, don't just assume it's going to be faster, time it, set a stopwatch, run it, time it, try it, experiment, and just do everything you can to squeeze every last ounce of performance out of a system is something that is missing from today's world, which is very Python and JavaScript, where it's like performance, what's that? Python is like layer after layer removed from the hardware, whereas Abrash is like, look, if we use this register, we can enable a graphics mode that's not supposed to be possible, and and they did. Like they would literally like send commands to like the video card that were undocumented and like enable a double resolution mode and things like that. And a lot of that is kind of dated. Like I said, like who cares? Like none of that's an issue these days. But that philosophy that he has, and so again, that book is called Abrash's Black Book. If you actually try buying it these days, I think it's actually redonkulously expensive. Let's see. $177 for the paperback. Yeah. So that's how good it is. Like you can see that rating there. Like it is one of the most important books in graphics of all time. But you can just get it for free. So you go to this website here. I'll post this in chat. It is ancient wisdom, but like rules for building high performance code. Know where you're going. Have a map. Know when to turn on juice, and sometimes you don't need to optimize, right? And so assume nothing, you know, test it, test, time it, test. And then these things like wait states, like these things are the 8088, like, yeah, I need to know that maybe as much. Speed up C with assembly. It's my readers gave me. Pushing 486 to the limits, like that. Probably not. But again, the philosophy that he brings to it is really good. So you can probably skip, you know, the higher 256 whole colors. Oh my gosh. Higher resolution 360 by 4. Yeah, that kind of stuff. Maybe not, but they're definitely like I would definitely like at least skim it. More modern stuff that are along the lines of what we're doing. Computer graphics from scratch by Gambetta. This is a No Starch Press, I believe, book. Is it? Yes, No Starch Press. One of my favorite presses. Computer graphics from scratch, and this will walk you through how to do reflections and how to do colors and how to do vector math and how to fill a triangle. Oh, look at that. That's literally going to be your next week's assignment. And it's a short book. It's very readable. This is a great book. Less readable books that are still good. This book here is sort of the standard textbook in computational geometry, and that is things like how do you make a BSP tree, right? And it's got pseudocode right there on how to make a BSP tree. It's more academia-ish. It's not as readable as the Gambetta book. Oh look, here's polygon triangulation. This is literally your homework assignment for today, right there. Given a bunch of points, how do we split it into triangles? Another book that is really good. It's the DeWolf book. That's what I'm thinking of. I know I'm misremembering the name. I'll look it up. There's a there's a few like standards like graphics textbooks. I have it on my computer here somewhere. Yeah. Can you please type the names of those? Yes, I'll type it up. Computational Geometry by DeBerg and et al. Computer Graphics from Scratch by Gambetta is really good. That's just a great introduction to everything graphics. Lines and reflections and all that kind of stuff. Ray tracing in a weekend is something I want to do with you guys. So this is a famous series by Shirley, and basically has you creating a ray tracing engine in a weekend. And it sounds impossible until you realize the starting ray tracer is not. It's not really. It's not exactly correct. You know, it's sort of pretending to a certain extent to be an engine, but you can still get ray tracing done in a weekend. And click on that, and then it runs you through the whole thing. Yeah. And this is one of these classic things that I think everybody should do. Another one is so like just the OpenGL or an OpenGL. Yeah, this is another great site where you can like learn how to do 3D programming, stuff like that. Graphics Gems is another one. GPU Gems. Yeah. Post that as well. Yeah, the little faces. Yeah. There's a lot of really good references out there. I've got some on Kindle as well. Kindle. So this is by a professor, I believe, at USC, if I remember correctly. It's using a library called the SDL. It's called Game Programming in C++. Let's see if I can find the table of contents here. So this is Madhav. Link these. You don't want to just read it. C++. It's another great one. Let's see. Yeah, I can put these into a resource for you. So that thing there, the game programming in C++, that one uses the SDL framework, I guess you'd call it. It's what Valve uses to do their source engine. It's sort of the layer between you writing code and like triangles appearing on the screen. Last semester we did some work with SDL. Mathematics. Oh, really? Another one is the Eric Lingiel book, Mathematics for 3D Game Programming and Computer Graphics. Sunday's Practical Geometry Algorithms. Gregory's Game Engine Architecture. There's just a lot of good resources out there. And if you're serious about such a good book, it doesn't even appear. Okay. So if you're serious about becoming like a graphics programmer, at least pick one of those books and just like chew it. Like it's literally like all of them will sort of run you from like 0 to 60. I've got my own schema here. We're basically starting with points, moving to lines, then moving to triangles. Then we're going to fill the triangles. Then we're going to colorize the triangles. I'm sort of like giving you sort of the ground up experience of everything rasterization, and then we'll do and then RTX-on was ray tracing, basically how to cast rays into a world that has a BBH tree and intersecting things and stuff like that in it. So, but the goal being we're going to build our own renderer by the end of it. If I get them, it's not going to be obsolete in like a year. No, like some of these books have been out for like the basic principles about like how a reflection works and things like that. Like that, none of that changes. And then this book, like I said, this is like the standard textbook in computational geometry. So, how do you use spatial searching? Like how do you if you click on a spot on a Google map, how do you find the nearest city to it? Not as easy as it sounds. How do you Voronoi? Yeah, we're gonna do that in this class too. So, okay, they're definitely worth the investment. Yeah, all of them, all of the ones that I mentioned are good books. I've read, if not all of them, at least good chunks of them, and I can recommend them all. Like I said, if you want to get good at graphics programming, just pick one of those books and just run through all the code, make sure you understand it, and then you're gonna have a good understanding of it. Yeah, I mean, there's a reason why they're within arm's reach of my table right here. Like that's my bookshelf right there is the ones that I can reach over and pull out when I need to do something. Let's see if I have any others over here. How to lie with statistics. That's a good one. All right. So let's talk about triangularization. How can we... First thing maybe is like, maybe we need to talk about this. Struct triangle. What describes a triangle? You guys, how would you describe a triangle? A lot of different ways. Triangle representation. We haven't talked about this yet. How do you make a class that holds a triangle? 3 points in space, 3 lines, side, angle, side, angle, side, angle. Does that work? 3 vectors, 3 points. Okay. Yeah, so if we have a point class, struct point, double xy, keeping it simple here. Then we can have like point A, B, and C, something like that. There you go. There's a triangle. That's one of the ways you can represent a triangle. You despise angle, side angle, side. Yeah, or you just have 3 points. It's fine too. But is there a possibility you don't actually have a triangle? If you have 3 points. They can be collinear. They can be on top of themselves. Your triangle might actually just be a point, right? They could all be the same point. Yeah, exactly. And so right now I'm doing this in pods style, plain old data. But you should probably have a constructor or something that makes sure that it is not a triangle. Yeah. So how would you, like if we were to make a raster function, right? And the raster function is going to draw the triangle to the screen using the colors library. Okay. Or the colors library has the ability to draw points on the screen. And let's say we've got a function called void line raster. It takes point P1, point P2, and it, draws a line from P1 to P2, like the algorithm I had on the screen a second ago. Still on the clipboard? Not at all. GPU Gems is there now. Okay, so we'll just pretend that exists. You can find it in the recording of the stream here. So how do we raster a triangle if we're just doing wireframe? How do we do this? How do we draw the outline of a triangle? We got 3 points. We got a function to draw between 2 points. A to B to C to A. All right. Line raster A to B. A to B. And I've still got GP Gems in that guy. P1 to P2, P2 to P3, and P3 to P1. You concur. All right. Yeah, there you go. So that's all you need. We're not filling the triangle yet. That'll be next time. So, so the question is, given a cloud of points, right, down here in main, we're going to be like input a bunch of points. How do we split this into triangles? If we get 3 points, it's easy, right? Like there's our triangle. But if we get 4 points, you got to split the 4 points, assuming they're not collinear. You got to split the 4 points into 2 triangles. How do you do that? And how do you do it nicely is even harder, right? Because a lot of our algorithms don't work well if you have like needle. It's like if we have 4 points, form like a perfect square, it doesn't really matter, right? We can either split it that way, or we can split it that way. It doesn't really matter, right? But if you have like 1, 2, 3, 4, like this, it's much better to triangularize it like this than it is to triangularize it like this. And the reason for that is because you have these like really narrow, very small angle things, and you can start getting rounding errors and things like that, cause graphics distortions, things like that. Also, another reason why this is better, like imagine you are trying to interpolate weather forecasts, right? So these, this is actually like how weather data is held, right? Like you don't have temperature necessarily at every point in the world. What you have is like, okay, well, it's 70 degrees here in Fresno. It's 60 degrees at Tahoe. It's 10 degrees at Hume Lake, and it is 100 degrees in Vegas. Okay. I guess I'm just writing the first letter of each one. So if you have a triangle that looks like this, and I ask you what is the temperature here, you say it's probably 60-ish, maybe a little bit, I don't know, a little bit more, like maybe 68, something like that. If you have the triangle like this, then that point here is going to probably be 35 degrees, right? And so it's probably going to give you a better estimation for points in between when you have nice kind of round, round's not exactly the right word, but kind of fat triangles instead of these long, narrow ones. It makes the interpolation between them better. This is not conducive. Like you're going to get a point here that's like 68. You're going to get a point here that's like 10. You know, it's maybe 19, whatever. It's not. It just doesn't work very well. So there's a lot of reasons why we want to do triangularization. Weather forecasts and interpolation, things like that are one of them. You can try possibilities until you get the one that's the most equilateral. Okay. Pick an arbitrary point, use a cross product, sort them in a clockwise fashion. Okay. Get line on the first 3 points. Try to convert English and math into code is hard. Point distance. Well, what you could do is like if you don't really care about running time, you could look at the outer part you can usually figure out, right? You might have to do like a convex hull wrapping algorithm, which is beyond the scope of this course, or at least for now. Like if you had a point here, then you can just connect these guys like this, right? And then you need to triangularize this. This isn't a convex hull at all. And so what you can do is, like if you're here, you can just like connect all the outer ones and connect all the bottom ones. What you can do is like, all right, well, I can draw a triangle this way, I can draw a triangle this way. That's it. You got 2 open spots to split it. You can look at which one's going to create an angle that is like nicer. Like you can do this one, or you can do this one, or both. Honestly, though, I don't really care very much for this assignment. I just kind of want you thinking about this, like how you would go about splitting it, but I don't really care. All I want is this kind of wireframe, right? Given a set of points, basically the input is going to be something like this, right? You'd be given a set of points, and then I just want you to make triangles out of them any way you can. So a simple algorithm might just be like, draw a line from me to the next guy to the right. You can sort all the points left to right. Draw a line to one to the right. Draw a line to the person 2 to the right. You know that there are going to be no other points in between, right? Right, because you've sorted them left to right. So you've got point 1, point 2, point 3, point 4, and so you make a triangle out of 1, 2, and 3. Again, we're gonna just assume nobody's collinear, and then you can make a triangle out of 2, 3, and 4. Congratulations, you're a triangle. And are you going to get a great triangularization out of this? No, but it'll work. Okay. Does that seem reasonable enough to you guys? I just kind of want you thinking about, the splitting for now. But all you have to do for this assignment is, given a set of points, sort them left to right, make a triangle out of 1, 2, 3, triangle out of 2, 3, 4, triangle out of 3, 4, 5, and that should do it. So if we had a point here, then the next triangle would be that. We draw a straight line. Can't, apparently. Just focus on breaking the points into triangles. It's just, like I said, just sort them left to right. So given a bunch of points, how do we sort points from left to right? Here's a fun question. 4 minutes left. How do we sort these guys left to right? Along the x-axis. Yeah, sure. Check the x. All right. So bool operator less than const point Let me make this a friend even. Friend will operate. One const reference point. Sorry, const point. Reference p2. Return p1.x is less than p2.x. There you go. And now you can, if you have a vector of points, you can just sort it, right? So if you have a vector of points like this, vec, you just call vec.sort, or sorry, sort vec.begin, vec.end. Just like that. And that'll work. You know, so we're not going to get a compile error. It's because we've got a less than operator defined on it. That'll sort them all left to right. Take the first three, make a triangle out of them. Take the next 1, 2, 3, one triangle. 2, 3, 4, one triangle. 3, 4, 5. Is it going to be great? No, not at all. But you'll get something. Enough to get points. Enough to get points on this assignment. Bruce, you feel comfortable with this? So just do a little input phase, read some points in, and then just make a bunch of triangles, then call a raster on the triangle. All right. Pain is what you get. X like Twitter. We sort on Twitter, exactly. You'll try. Let's look at the starting code, see if there's anything I need to explain in there. I think there is triangularization. So, what is this thing here? First of all, what's the difference between a vec2 and a point? Absolutely nothing. What I was calling point a second ago is a vec2. It's literally the same thing. It's got an x and y location, aka a row and a column. Row is y, column is x. So maybe they're held in different order, but whatever. So what is this thing then? What is that? It's new. What is that? It's a TIE fighter. Yeah. Except I don't think we call it that. Yes, it is the spaceship operator, right? So the spaceship operator is something added to C++ and C++20. And it generates a less than operator, a comparison operator, not equals operator, greater than operator, whatever other combinations are left off. Less than or equal to, greater than equal to, comparison, not equal to. Makes all 6 of them. How? It first sorts on row, then it sorts on column. So this one is going to sort top to bottom instead of left to right. It makes no difference. Okay? And then we're going to make a deck out of the points. Why a deck? Well, remember, we're going to be making triangles using 3 at a time, right? So if we've got 10 points, we're going to make a triangle out of 1, 2, and 3. We're going to pop 1 off. We're going to make a triangle out of 2, 3, 4, then pop 2 off. Triangle out of 3, 4, 5, pop 3 off. Okay? So we're going to add points in the back, pop points off the front. Color. How do you sort colors? Well, this will first sort on the red value, then it will sort this on the green value, and then it'll sort it on the blue value. And A-style might not be aware of the spaceship operator, so it might put a space in there and cause your code not to compile. So be careful if you are using the compile shell script, which A-styles your code. So a U8, what is U8? These are aliases that you see in game development all the time. These are using typed defs. I typically don't use typed defs. I typically use using this keyword is the C++ version of this keyword, which is C. So if you want to signed 8-bit integer, I just call it an S8. If you want to sign 16-bit, S16, unsigned 8-bit, unsigned 16, unsigned 32, unsigned 64. These are superior to using int or long because on different platforms, longs will have different numbers of bits in them. So I think it is generally superior to just say, give me a 32-bit signed integer instead of an integer, just in case you happen to port your code to a system that has 16-bit ints or 64-bit ints or something like that. And so the reason why we do this is because now we can sort colors if we want. We can sort the vec2s if we want, because we've got a less than operator defined on it. And this is really neat. You can just say equals default, and it makes one for you. It makes one for you. So it's really cool. It just adds the ability to sort them for you and compare them, stuff like that. This is the size of the world, how many rows, how many columns, and that gets set down here. So here we've got auto temp rows, temp columns, get terminal size. And get terminal size is a function in my colors library that gives you how large the screen you're on is in rows and columns. And this thing here looks probably a little bit weird to you, doesn't it? This bit right here. If you've never seen a structured binding before, what this is doing is get terminal size is actually returning a struct. And then this thing here is actually splitting the struct into two just integers. And so this is an integer temp row, temp column. And then I set rows equal to temp row and columns equal to temp column. So this is returning a struct, and it's actually unpacking the struct and splitting it into two integers. It's kind of cool. It's a neat feature in C++ 17. And the format for that is auto square bracket, variable 1, variable 2, variable 3 if you have one, close square bracket, equals something that returns a pods. It doesn't work with a class, but if you have plain old data returning two public member variables, the first member variable goes into this guy, temp row, the second member variable goes into temp C. Super useful function. It's not like you can just make a struct and then copy it out, but I like it. I reduced the number of rows by 1 so we don't ever print on the bottom row because that causes Putty to scroll the screen up. I resize the world so that it's got rows and columns equal to the rows and columns of, this is just like a 2D array. And so it's got 1 point for every point on the screen. I turn on low rent and curses mode. Megan says that I cast shade on other people sometimes, and I'm casting shade on myself this time. So my colors library is a low rent and curses. And so I'm turning on raw mode, which means you don't have to hit return to do input. Turning off the cursor, turning on the mouse. So you can click on the screen with your mouse. And that's kind of cool. Every time you click, this is a callback. This is something called a callback, or an event handler. And so basically every time the user clicks the mouse, it's going to call this function called mouse handler. And mouse handler is somewhere. I don't know where it is. It'll call that function. And that function will receive essentially the row and column that the mouse was clicked on. So, and then it goes into an infinite loop where basically it is just waiting for the user to do something. Every time the user clicks, then there's not even any code in here to handle clicks. When the user clicks, it just calls that callback automatically. And that's your starter code. This at exit is another callback, so that when the program quits, it calls this function. And so this function cleans up, because we're in like full screen mode, the cursor's turned off, we might have like background colors set. It screws up your terminal if you don't have this. So when we quit, then it calls this function, and this function like clears the screen, resets the colors, puts the cursor back on, stuff like that. And if we hit Control-C to get out, if you hit Control-C, normally I believe bailout is not going to get called. So I have a interrupt handler, another callback that says if the user Control-C's out of this, call bailout, basically. So the interrupt handler, I don't know where this is either. Is there like a different file in here? Oh yeah, okay. So bailout turns mouse off, turns the cursor back on, clears the screen, resets the colors, clears. The interrupt handler, if you hit Control-C, it just calls exit, and exit calls bailout, because bailout is a callback set on at exit. And then the mouse handler, every time you click, it just sets, there's a global variable, last row and last column. These variables get set to be whatever the last click row and column was. What library is at exit? That is in the standard library. So the standard library is C standard library, in fact, not even C++. The C standard library allows you to register a function to run when your program terminates. And so this is really useful if you have like a networking program and you need to like close the socket. If you have open files, things like that. Typically in C++, we handle those sorts of things with constructors and destructors. But for a situation like this, where somebody could just Control-C out, I have a function that says, okay, let's put everything back the way it was. Let's reset the colors and turn the cursor back on. Otherwise, just, your putty's kind of bright red, no cursor, you can't see anything. So C stdlib, yeah. Mm-hmm. So you can include stdlib.h. That's fine. The more C++y way of including it is to include C stdlib no.h, and that is the version that most people would use these days. And that's it for IS50B. Thanks for coming out, guys. Have fun making some triangles. Make a triangle class, make a point class if you don't have one, and just use my line rasterization algorithm, raster some triangles on the screen. Have fun with it. All right? It's fun. It's fun. When is it due? I was going to say on Tuesday. Like, it's the next class. But also if you guys ever miss any of the homework assignments in this class, just talk to me. You should make it up. Don't not do stuff. Also, so for you guys in 26, it's due on the same day as inventory. Can you make up today's homework? Yeah. Like if you don't get it done, just get it to me. And there we go. All right, so I got to switch over to 50A now. All right, see you 50B people.